Hello students, today's agenda is to check your homework. You're going to be looking at vertical stretches and compressions, and you will be able to do 7.4. Today students will be able to identify the effect of vertical stretches and compressions. And when we're talking about vertical, it's when something goes up and down. That's vertical. And vertical stretch means like pulling up and down. So let me give you some examples, and then I usually use whatever I have in hand. And I have here a little poncho that I can use just to demonstrate what I'm saying. But let's see. If we have y equals x, the graph that produces is a line. And you saw this in quarter one. So you just have a regular line. But then, if you have y equals 2x, that means that each point you're multiplying by 2. And so, instead of being, like if you have 1 for x and 1 for y, okay? But then you're multiplying that x by 2, meaning that you have 1 for x, but then multiply the x 2 times 1, that will give you 2. So you're stretching that point right there. Now, before you had 2, 2, right? You had 2, 2 for the point in the original graph, but when you multiply the x times 2, so it's 2 for x, but my y is going to be equals to 2, the value of x, which is 2 times 2 would be 4. So it's going to be, instead of 2, it's going to be 4. So you're stretching that point. 3, initially, or in the original graph for y equals x, is 3, 3. But now that you're multiplying my x by 2, that means twice as much. So that will be 6. So my new graph, basically, oh, and let me do a couple in the negative so that you can see. -1, -2, -3, -1, -2, -3. So before it was -1, -1, -2, -2, -3, -3. But again, that's the values of x, right? If we plug in for the new equation, it would be -1 for x. So I plug in -1 in here. 2 times -1 is -2. So my y equals -2. So my new point would be here. Instead of here, is stretching vertically, up and down. -2 times 2 is -4. So about here. And -3 times 2 is -6, so about here. So my new graph for this equation would be this right here. Okay? And so whenever the coefficient of x is a whole number that is bigger than 1, that means that there is a vertical stretch, okay? So let me write that down. If we multiply by a number, and if we multiply x, basically, if we multiply x by a number greater than 1, meaning 2, 3, 4, 5, 6, 7, 8, then the graph stretches. And stretches means it gets taller, Okay, it gets taller. Each point gets taller, and therefore it seems like it also gets skinnier. So let me show you what I meant with the fabric here. Hopefully it's not gonna look awkward, but this is my little poncho that I have. What happens to each point when I stretch it vertically? If you notice, it gets taller and skinnier at the same time, okay? Again, this is regular. I stretch it, and look at each of those sections. It gets taller, but then at the same time, it looks like it gets closer to Y, if we're talking about. Look at my graph. I stretch it. It looks skinnier and taller, okay? Okay, what if I multiply, and I'll do it in the same, times 4. I'm just gonna use a different color. So if I multiply 1 times 4, it's not gonna be 1 or 2, but now it's going to be 4. 2 times 4 is gonna be 8. So about here. 3 times 4, that will be 12, which is gonna be way up there, okay? And it would be the same thing here. -1 times 4 is -4. -2 times 4 will be -8, so about here. And so if you notice, the bigger the number, the more it stretches, right? The taller my graph gets and closer to Y because of that. Okay, what happens when you multiply by a fraction? So let me redo this. Again, our regular graph. This would be Y equals X. But when we multiply by 1/2, that's called a compression. Oh, sorry. So this was a vertical stretch, okay? I'm gonna write here vertical stretch. In here, this is gonna be a vertical compression. And so what this means is that each point, for example, for this one, if X is 1, since Y is equals to X, Y is 1, okay? If X is 2, Y is 2. If X is 3, since Y is equals to that, then Y is 3. And that works the same for the negatives, okay? But in here it says, now I want you to graph Y equals 1/2 of X. So if X is 1, my Y will be half of that 1, which is 1/2. If X is 2, my Y will be equals to half of 2, meaning 1. If X is 3, 1/2 of 3 will be 1.5. And if X is 4, my Y will be 2. Whoops. Okay, so that's where my line would go. Basically, whoops. All of these points are being compressed because you get only half of what you had before for each value of y. And in here, it will be in the similar way. If x is -1, half of -1 is -0.5. Half of -2 is -1 for y. If x is -3, it's going to be -1.5, and so on. And so if you notice, now with this, it's a little bit more difficult. I was going to use this wall to show you what happens when you compress. So each point, if I have a point here, when I compress vertically, each point goes closer to x, but at the same time, what happens on the outside of the ball? Look at that. It kind of widens, right? But basically, what's going on is that each point gets closer to my x, okay? Each point gets closer to my x. Okay, and again, if we do a number, for example, if I have, instead of 1/2, maybe y equals 1, it's gonna be hard to show you, maybe 1/4 of x, and I'll just use the bigger numbers. So if x is 2, 1/4 of 2 would be, oh my goodness, it would be half. Okay, so about here, that means that it's 1/4 of that 2. You divided the 2 by 4 is 0.5, so it's right here. I'm gonna use the 4. If I have 4 divided by 4 is 1, so it's gonna be 1/4 of 4 is 1. And on the other side, it's gonna be the same. For 2 will be 1/2, and for 4, for -4 actually, it will be 1. Okay, so the bigger the denominator, the shorter my line will be, or my points will be. Okay, again, we have, let me see if I can fit both of these. We have vertical stretches, which makes the graphs taller, and vertical compressions when it's a fraction, and it makes every point shorter. I'm not going to ask you to do specific. I just want you to know the general, okay, that this is going to be happening in my graph, and so that's what I want you to show me. Okay, what about if we have y equals x, again, the original, and we have my regular line. But then for the new graph, we're gonna put y equals -x. Y equals -x. And so, if before y is the same as my x, is gonna be 1, then I have 1 for y. If my x is 2, then I have 2 for y. 3 for y. Okay, because they're exactly the same. But now, what this is saying is I'm gonna get the negative of x. So if I have +1, I'm gonna get the negative of that one, so it's gonna be -1 for y. If I have 2, I have -2 for y. 3, I have -3 for y. And in the opposite direction is, if I have -1, I have positive, because negative from here and the -1 in here, it's going to be negative times -1 is +1. -2, +2, and 3, and so on. Okay, so whenever we have a negative, Basically, it's like if you have a mirror on the x-axis and this mirrors to the bottom, and this section of the graph reflects on top of it, okay? So it's kind of like a reflection, basically. This reflects down here and this reflects up here, okay? Again, when we have a negative, we have my x-axis being the mirror, the line of reflection. Okay. Now what if I have, let me see, with a different color, I'll use blue. Y equals negative 2x. Well, we have two different transformations going on. We have a stretch and a reflection. So the stretch will look something like this, right? It's gonna stretch, but then it's gonna reflect, so it will be reflected. Remember that this is closer to y because of the tallness. So it gets closer to y. And I don't want you to do specific points, but it would be something like this. Okay, because you're multiplying by 2, it's just twice as big. So it stretches, but it also reflects. If this is my original, my stretch will be like this, but then if the negative reflects on the line of reflection, which is the x-axis. Okay. We can call this like an upside down. Whenever we have a negative, upside down. So we'll see it. It's going to be a little bit more clear when we do. I'm going to show you with, what do you call a cube, okay? Okay, so let's use, now I want to remind you that when we have y equals x, it's just this type of graph. It's just the type of graph that we have. If we have y equals x squared, it just means that we have a parabola. And if we have y equals x cubed, this is a review from one of the modules that we have, then this is the type of graph that you get. If we have the absolute value of x, then the type of graph that it creates is like this. And if we have square root of x, then the type of graph that you will get is only half of the graph, because there is not such a thing as negative x inside of the square root, so we cannot have something like this. Okay, so this is just for general reference, because you're going to be looking at different graphs and then you might get confused, but it's just depending on what type of graph you get in here, that's the shape that you will get on the graph. Okay. Okay, so now we're going to be working with y equals x cubed. And so the graph that you have, the mother graph, is like this. Okay, and the reason is because you get 1 cubed will be 1, 2 cubed will be 2 times 2 times 2, which is 8, 3 times 3 times 3 is like 27, so that's why it increases slowly and then fast, okay? And the same on the other direction. But what if we want to graph y equals 2x cubed? So remember that we were doing point by point before? Oh, and we can do it in here. In reality, I don't want you to stress too much about each point. In reality, what I want you to get is that what is it that is going on when we're multiplying by 2? Well, it's stretching vertically. And again, when we stretch vertically, it gets taller and closer to y, okay? So each point gets taller and closer to y, okay? It doesn't matter, you don't have to be exact, but I want you to know that this is what happens. It stretches, okay? So my new graph would be something like this. Okay, and you don't have to be exact with the points. I just want you to understand what's going on or what happens or what is the effect of vertical stretches and vertical compressions. Okay, what if I have y equals 1/2 of x cubed? So I'm gonna do the original here. Okay, and remember that when we multiply by a fraction, it's a compression, so each point gets shorter. Again, it doesn't have to be exact. Okay, each point gets shorter or closer to x, and so my graph would look something like this. Again, you don't have to be exact, it's just you understanding the effect of multiplying by a whole number and a fraction. What if I have y equals negative x cubed? Well, let me draw my original in black. And you can notice that this is not perfect, but and actually this should be a different color so I don't get too confused. So my original is my y equals x cubed. Negative, it just means this is my line of reflection. This is like my mirror. My mirror makes this go here. And this mirror also makes this go over there. Okay, so something like that. This goes down, this goes up because the mirror is right here. Okay? Let me do y equals negative 2x cubed. So in here, two things are going on. I'm multiplying by 2, which is going to make my graph taller. But then I'm also multiplying by a negative, which makes this the mirror. Okay, it reflects upside down. It's like upside down. It goes upside down. Okay, so let me, again, I should have written this with a different color so that you know that this is the actual final effect. So first, you can just kind of like say, oh, times 2, that means that it goes taller, right? It stretches. But then this makes it upside down, so instead of going up, it's gonna open down, but skinnier, right? It looks taller, which makes it also skinnier. And this goes up. It's gonna look like this, closer to y, farther away from x, but at the same time upside down because of the negative. Okay, one more example. This is my original. But now I have y equals negative 2/3 x cubed. This is gonna make it shorter. It's gonna compress it. Each point goes tinier, so something like this. Whoops. I should just do dotted line. Why? Because I also have the negative. Okay, this is not the actual graph. It's just kind of like dotted. That will be only multiplying by 2/3. But then there is a mirror. So instead of going up, it's going to open down. Look how it looks shorter, closer to x. Whoops. I just mirrored that. And this is going to reflect on top because it's upside down. Okay, so this is the real deal. Okay, so maybe you have not seen something like this before, so you might want to watch the video several times to make sure that you understand what's going on. Again, this is not the real, it's just multiplying by 2/3, but you still need to do the reflection. So it would kind of go like that. If you just multiply by 2/3, right, it will compress it. But then the negative means you switch to the bottom and the bottom to the top, but of the compressed graph. Okay, so I hope this is not too confusing. And it's kind of a long video, sorry about that, but I hope now you can do 7.4.